somewhere deep within the Milky Way galaxy, hidden inside a vast glowing cloud of gas and dust, there is a star that astronomers have been watching for nearly 2 centuries. Its name is Eta Carinae. At first glance, it appears to be just another distant star among billions in our galaxy. But Eta Carinae is far from ordinary. It is one of the most massive and unstable stars ever discovered, a cosmic giant that has already erupted violently in the past. In the mid-1800s, this star suddenly brightened so dramatically that it became one of the brightest objects in the entire night sky. Astronomers at the time had no idea what they were witnessing. The star had unleashed an enormous eruption, throwing huge clouds of gas into space and creating the glowing nebula that still surrounds it today. And yet, despite that incredible explosion, the star survived. But many scientists believe Eta Carinae may still be approaching the final stage of its life. One day, this unstable giant could collapse and explode in a supernova, an event powerful enough to briefly outshine entire regions of our galaxy. No one knows exactly when it will happen. It could be thousands of years from now, or far sooner than we expect. Tonight, we're going to explore the strange and fascinating story of Eta Carinae, a star that lives on the edge of destruction. And if you enjoy quiet journeys through the mysteries of the universe, consider subscribing to Theories Before Sleep, where we explore the cosmos, one story at a time. To understand why Eta Carinae fascinates astronomers so much, we first need to travel far beyond our own solar system, deep into one of the most active stellar regions of our galaxy. Our destination lies roughly 7,500 light-years from Earth, in the southern sky, inside a vast and turbulent cloud of gas and dust known as the Carina Nebula. The Carina Nebula is one of the largest and brightest stellar nurseries in the Milky Way. It stretches across hundreds of light-years and contains enormous clouds of hydrogen gas slowly collapsing under gravity to form new stars. In many ways, it is a cosmic factory where some of the most massive stars in our galaxy are born. If we could somehow travel there, the view would be extraordinary. Instead of the quiet darkness we see in most regions of space, the Carina Nebula would appear alive with glowing clouds of pink, orange, and blue gas illuminated by powerful radiation from young stars. Massive pillars of gas would tower across space like cosmic mountains. Shockwaves from stellar winds and explosions would ripple through the nebula, constantly reshaping its structure. At the heart of this violent environment lies Eta Carinae, and compared to the other stars around it, Eta Carinae is truly colossal. Most stars in our galaxy are relatively modest in size. Our own Sun, for example, is considered a medium-sized star. It has been steadily burning hydrogen for about 4.6 billion years, and it will likely continue doing so for another 5 billion years before eventually expanding into a red giant. But Eta Carinae exists on a completely different scale. Astronomers estimate that the main star in the Eta Carinae system contains more than 90 times the mass of our Sun. Some earlier estimates suggested it may once have been even more massive, possibly exceeding 150 solar masses before losing huge amounts of material during violent eruptions. Stars this massive are incredibly rare. In fact, only a tiny fraction of stars in the Milky Way ever reach such enormous sizes. And because of their extreme mass, these stars live very different lives compared to smaller stars, like our Sun. The reason lies in the intense pressure at their cores. Inside every star, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. This energy pushes outward while gravity pulls inward. As long as these two forces remain balanced, the star remains stable. But when a star becomes extremely massive, the pressure and temperature at its core become far more extreme. In the case of Eta Carinae, the core temperature may reach tens of millions of degrees. Under these conditions, nuclear reactions occur at an astonishing rate. While the Sun burns its fuel slowly over billions of years, massive stars burn through their nuclear fuel thousands of times faster. It is a bit like comparing a candle to a blowtorch. The candle burns slowly and steadily. The blowtorch burns incredibly bright, but only for a short time. Eta Carinae belongs to the blowtorch category. Because of this rapid fuel consumption, astronomers believe Eta Carinae may already be nearing the final stages of its life, despite being only a few million years old. That may sound like a long time, but in cosmic terms, it is incredibly young. The Sun is more than 4 billion years old. Compared to that, Eta Carinae is practically a newborn star that is already rushing toward its dramatic end. Yet what makes Eta Carinae even more intriguing is that it is not just one star. It is actually a binary system, meaning two massive stars orbit each other in a tight and complex gravitational dance. The largest star, the one responsible for most of the dramatic events astronomers observe, is often referred to as Eta Carinae. This giant star dominates the system. It is incredibly luminous, shining with a brightness that may be 5 million times greater than the Sun. But orbiting it is a second star known as Eta Carinae b. Although smaller than its companion, this second star is still enormous by normal standards. It may contain around 30 solar masses and produces extremely powerful stellar winds. Together, these two stars create one of the most energetic stellar systems in the Milky Way. Every 5.5 years, the two stars move close together in their orbit. When this happens, their powerful stellar winds collide with tremendous force. These winds consist of streams of charged particles blasted away from the stars at speeds reaching thousands of kilometers per second. Where these winds collide, enormous shock waves form. These shock waves heat surrounding gas to millions of degrees, producing bursts of X-rays and other high-energy radiation that astronomers can detect from Earth. In fact, by observing these periodic changes in radiation, scientists were able to confirm that Eta Carinae is a binary system rather than a single star. But the story of Eta Carinae becomes even more dramatic when we look at the enormous cloud of gas surrounding it. Today, if we observe Eta Carinae through powerful telescopes like the Hubble Space Telescope, we do not see the star clearly. Instead, we see a strange and beautiful structure called the Homunculus Nebula. This nebula looks almost like a giant hourglass made of glowing gas. Two enormous lobes of material extend outward from the center, expanding slowly through space. Each lobe contains massive amounts of gas and dust that were violently ejected from the star. The Homunculus Nebula did not exist long ago. In fact, It was created by a massive eruption that occurred in the 19th century. At the time, astronomers had only just begun carefully recording changes in the brightness of stars. And when Eta Carinae suddenly brightened dramatically, it immediately caught their attention. In the year 1837, the star began increasing in brightness. Over the next few years, it became brighter and brighter until it eventually became the second brightest star in the entire night sky, surpassed only by Sirius. Imagine the shock of astronomers witnessing such a dramatic transformation. For centuries, the stars had seemed permanent and unchanging. Yet here was a star suddenly blazing brighter than almost anything else in the sky. The eruption continued for nearly 2 decades, releasing an enormous amount of material into space. During this event, Eta Carinae may have ejected more than 10 times the mass of our Sun. That is an almost unimaginable amount of material. To put that into perspective, if our Sun suddenly lost 10 solar masses, it would essentially be destroying itself. Yet somehow Eta Carinae survived. When the eruption finally subsided in the late 1850s, the star faded again, becoming much dimmer than it had been before. But the damage had already been done. The enormous clouds of gas expelled during the eruption expanded outward, eventually forming the Homunculus Nebula we see today. Even now, more than 170 years later, the nebula continues to grow. The gas is still expanding at speeds of hundreds of kilometers per second, slowly drifting farther into space. This event, known as the Great Eruption, remains one of the most mysterious stellar outbursts ever observed. It was not a supernova, because the star survived, but it was far more powerful than the typical eruptions seen in unstable stars. Astronomers sometimes describe it as a supernova imposter. In other words, it looked like a supernova, but it wasn't. The true cause of the eruption is still debated today. Some scientists believe it may have been caused by instabilities inside the massive star itself. Others suspect the close interaction between the two stars in the binary system may have triggered the explosion. There are even theories suggesting that a third star once existed in the system and may have merged with Eta Carinae during the eruption. Whatever the cause, the Great Eruption revealed something important. Eta Carinae is an extremely unstable star, and if it was capable of releasing that much energy without dying, then its eventual death could be far more dramatic, because massive stars like Eta Carinae do not end their lives quietly. When they finally exhaust their nuclear fuel, gravity wins the battle inside their cores. The star collapses inward, triggering a catastrophic explosion known as a supernova. In the case of a star as massive as Eta Carinae, that explosion could be among the most powerful events in our galaxy. But before we can understand how Eta Carinae might eventually die, we first need to understand something even more extraordinary. Eta Carinae is not just massive. It may belong to a special category of stars known as luminous blue variables, some of the most unstable and violent stars in the universe, and their behavior pushes the limits of what stars can survive. In the next part, we'll explore what makes these rare stars so unusual and why Eta Carinae may be one of the most dangerous stars in our galaxy. Eta Carinae is not just remarkable because of its size. What truly sets it apart is the type of star it appears to be, Astronomers classify Eta Carinae as something known as a luminous blue variable, often abbreviated as LBV. These stars belong to one of the rarest and most unstable categories of stars ever discovered. In fact, there are only a handful of confirmed luminous blue variables in the entire Milky Way galaxy. Yet despite their rarity, these stars play a crucial role in shaping the cosmic environments around them. To understand why, we first need to explore what happens when a star becomes extremely massive. Most stars form when clouds of gas collapse under gravity. As the gas compresses, it heats up until nuclear fusion begins in the core. At that point, the outward pressure from fusion balances the inward pull of gravity, creating a stable star. But when a star becomes extremely massive, dozens or even hundreds of times more massive than our Sun, this balance becomes much harder to maintain. The core of such a star burns at extraordinary temperatures, and the amount of energy being produced is almost unimaginable. That energy does not simply remain inside the star. It pushes outward in the form of intense radiation pressure. Radiation pressure is the force exerted by light itself. In small stars like our Sun, this pressure is relatively minor compared to gravity, but in extremely massive stars, radiation pressure becomes so powerful that it can actually begin to push the outer layers of the star away. This creates a delicate and unstable balance. Gravity is constantly trying to hold the star together. Meanwhile, radiation from the core is trying to tear the star apart. Luminous blue variables exist right at the edge of that balance. They are stars that are so massive and so luminous that their own radiation almost overwhelms their gravity. Because of this, their outer layers become extremely unstable. Instead of remaining calm and steady like our Sun, these stars undergo violent cycles of expansion, contraction, and eruption. Sometimes the star may suddenly grow brighter. Other times, it may shed enormous amounts of mass into space. And occasionally, the star may erupt in an explosion so powerful that it resembles a supernova. Yet somehow, the star survives. Eta Carinae is perhaps the most famous example of this phenomenon. Before the Great Eruption in the 1800s, the star was already known to be bright. But after the eruption, astronomers realized they were observing something extraordinary. The star had ejected enormous amounts of material without destroying itself. Events like this are known as giant eruptions, and they are one of the defining characteristics of luminous blue variable stars. During a giant eruption, a star may lose a significant portion of its mass in a relatively short time. Massive clouds of gas are blasted into space, forming expanding nebulae around the star. The Homunculus Nebula surrounding Eta Carinae is one of the most spectacular examples of such an eruption. But Eta Carinae is not the only star known to behave this way. Another famous luminous blue variable is P Cygni, a star located about 6,000 light-years from Earth. P Cygni underwent a major eruption in the 17th century that dramatically increased its brightness before gradually fading again. Although P Cygni is impressive, Eta Carinae dwarfs it in both mass and violence. The Great Eruption of Eta Carinae released far more material and energy than any eruptions seen from P Cygni. Because of this, Eta Carinae is often considered one of the most extreme luminous blue variables ever observed. To truly understand the scale of these eruptions, we need to consider how much energy they involve. During the Great Eruption, Eta Carinae may have released as much energy as a typical supernova, yet it did not destroy itself. Instead, the explosion blasted enormous shells of gas into space while leaving the core of the star intact. These expanding shells are what eventually formed the glowing lobes of the Homunculus Nebula. Even today, astronomers can observe the material racing outward at hundreds of kilometers per second. The nebula itself contains huge amounts of dust and gas, making it both beautiful and scientifically valuable. Because the eruption happened relatively recently in astronomical terms, the Homunculus Nebula provides a rare opportunity to study the aftermath of such a violent event. With telescopes like the Hubble Space Telescope, scientists have been able to examine the nebula in extraordinary detail. Images reveal complex structures, ripples, filaments, and dense clumps of material, suggesting that the eruption may have been far more chaotic than originally thought. Some researchers suspect that multiple explosions occurred during the Great Eruption rather than a single event. Others believe the interaction between the two stars in the Eta Carinae system may have played a major role. Remember that Eta Carinae is not a solitary star. It has a companion star orbiting it every 5.5 years. This companion star produces extremely fast stellar winds, streams of particles traveling at thousands of kilometers per second. When these winds collide with the slower but denser winds from the larger star, enormous shock waves form between them. These collisions produce intense bursts of X-rays and high-energy radiation. By observing these X-rays, astronomers can track the orbital motion of the stars and study the violent interaction between their stellar winds. In fact, the region where these winds collide may be one of the most energetic environments in our galaxy. Imagine two enormous cosmic hurricanes colliding at thousands of kilometers per second. The resulting shock waves heat gas to temperatures of millions of degrees, creating a turbulent region filled with high-energy particles. But even this dramatic interaction may not fully explain Eta Carinae's instability. There may be deeper processes occurring inside the star itself. One of the key factors may be something known as the Eddington limit. The Eddington limit represents the point at which the outward pressure from a star's radiation becomes equal to the inward pull of gravity. If a star exceeds this limit, radiation pressure can begin blowing away its outer layers. Massive stars like Eta Carinae operate extremely close to this limit. In some cases, they may even exceed it temporarily. When that happens, parts of the star's outer atmosphere can become unstable and begin escaping into space. This may be exactly what happened during the Great Eruption. The star may have become so luminous that radiation pressure essentially pushed huge portions of its outer layers away. The result was a massive outflow of gas that formed the Homunculus Nebula. But this raises an important question. If Eta Carinae already lost such an enormous amount of mass during the Great Eruption, why didn't it explode completely? The answer may lie in the internal structure of the star. Even though the eruption expelled vast amounts of material, the core of the star remained intact. As long as nuclear fusion continues in the core, the star can survive. But the loss of mass may have pushed the star closer to its final fate. Massive stars evolve extremely quickly. Instead of spending billions of years burning hydrogen like the Sun, they rapidly progress through several stages of nuclear fusion. After hydrogen is exhausted in the core, the star begins fusing heavier elements such as helium, carbon, oxygen, and eventually even heavier elements. Each stage burns faster than the last. By the time a massive star begins producing elements like silicon and iron in its core, the process may last only days or weeks. When iron finally accumulates in the core, fusion can no longer produce energy. At that moment, gravity takes over. The core collapses, triggering one of the most powerful explosions in the universe, a supernova. Eta Carinae may still be thousands of years away from this final collapse, but given its extreme mass and instability, astronomers believe it is almost certain to end its life in some kind of catastrophic explosion, and because of its unusual properties, that explosion might not be an ordinary supernova. Some scientists believe Eta Carinae could eventually produce something even more extreme, a hypernova, or possibly even a gamma-ray burst, among the most energetic events known in the universe. But before we explore those possibilities, we need to understand what happened during the Great Eruption in much greater detail, because the explosion that created the Homunculus Nebula may offer important clues about how Eta Carinae behaves and how it might eventually die. In the next part, we will take a closer look at the Great Eruption of the 19th century, one of the strangest stellar events ever recorded in human history. In the early 19th century, long before modern telescopes and space observatories existed, astronomers relied on careful observation and handwritten records to study the night sky. The stars were considered stable, distant points of light, unchanging and eternal. But in the year 1837, something extraordinary began to happen in the southern sky. A star located in the constellation Carina started to grow brighter. At first, the change was subtle. Many stars vary slightly in brightness, so the early increase may not have seemed alarming. But over the following months, the star continued to brighten. And it did not stop. Night after night, observers noticed that the star was becoming more luminous. By the late 1830s, it was already brighter than most stars in the region. Then the eruption intensified. By 1843, the star had become one of the brightest objects in the entire night sky. Only Sirius, the brightest star visible from Earth, shone more brightly. For a star located 7,500 light-years away, this was astonishing. To appear so bright at such a distance meant that the star itself must have been producing an enormous amount of energy. Astronomers at the time had no explanation for what they were seeing. The concept of stellar explosions had not yet been fully understood. Supernovae were poorly documented, and the mechanisms that power stars were still unknown. All they could do was record the brightness and continue watching. But the eruption did not behave like a normal supernova. A true supernova is a brief but catastrophic explosion. A star suddenly brightens for weeks or months and then fades away as the star itself is destroyed. Eta Carinae behaved differently. Instead of exploding once and disappearing, the star remained bright for nearly 2 decades. From roughly 1837 to 1858, the star went through a prolonged period of violent activity. During this time, enormous quantities of material were blasted away from the star into surrounding space. The event eventually became known as the Great Eruption, but it was not until the 20th century that astronomers began to understand how extraordinary it truly was. Modern studies suggest that Eta Carinae expelled more than 10 times the mass of our Sun during this eruption. To appreciate how dramatic that is, consider our own Sun. The Sun loses a small amount of mass over time through the solar wind, but it does so gradually over billions of years. Eta Carinae ejected an amount of material greater than the mass of our entire Sun in just a few decades. The energy involved was staggering. Some estimates suggest that the eruption released energy comparable to a supernova, yet somehow the star itself survived. Because of this, astronomers sometimes describe the event as a supernova imposter. In other words, it looked like a supernova from a distance, but it was not the final death of the star. Instead, the eruption created one of the most unusual structures in space. Today, surrounding Eta Carinae is a vast expanding cloud of gas called the Homunculus Nebula. When viewed through powerful telescopes, the nebula appears as two enormous lobes of glowing material extending outward from the central star. The shape resembles a cosmic hourglass or two giant bubbles expanding in opposite directions. Each lobe is filled with dense gas and dust that was violently expelled during the eruption. The nebula is enormous. From one end to the other, it stretches across about 1 light-year of space, and it is still expanding today. Measurements show that the gas in the Homunculus Nebula is moving outward at speeds of over 600 kilometers per second. Even after more than 170 years, the material continues drifting farther away from the star. This expansion allows astronomers to trace the origin of the nebula back to the exact period of the Great Eruption. By measuring how fast the gas is moving and how far it has traveled, scientists can effectively rewind the event like a cosmic movie. All the evidence points back to the dramatic explosion of the 1840s. But despite all these observations, the true cause of the eruption remains a mystery. Several competing theories have been proposed. One possibility is that the eruption was caused by instabilities inside the star itself. Massive stars like Eta Carinae operate very close to the Eddington limit, the point where radiation pressure becomes strong enough to push material away from the star. If the star briefly exceeded this limit, its outer layers may have become unstable and been violently expelled. In this scenario, the eruption would have been driven by the intense radiation produced inside the star's core. Another possibility involves the binary nature of the Eta Carinae system. Remember that Eta Carinae is not a single star. It consists of two massive stars orbiting each other every 5.5 years. Their orbit is extremely elongated, meaning that at certain points they pass very close to one another. During these close approaches, the gravitational interaction between the two stars becomes incredibly intense. Some astronomers believe that during the Great Eruption, the companion star may have plunged deep into the outer atmosphere of the larger star. If that happened, the interaction could have triggered a violent expulsion of material. Imagine two enormous stars colliding within a swirling cloud of gas. The gravitational disturbance alone could release an enormous amount of energy. There is even a third theory. Some scientists suspect that Eta Carinae may once have been part of a triple star system, In this scenario, a third star could have spiraled inward and eventually merged with the primary star. A stellar merger like this would release tremendous energy and could easily explain the massive eruption. If such a merger occurred, it would also help explain why the eruption lasted for so many years. The merging process might have destabilized the star for decades, causing repeated outbursts of gas and radiation. Unfortunately, because the event happened nearly 2 centuries ago, direct evidence for any of these scenarios is difficult to obtain, but the Homunculus Nebula provides valuable clues. Detailed images from the Hubble Space Telescope reveal that the nebula is not perfectly smooth. Instead, it contains complex structures, ripples, filaments, and dense clumps of gas. These features suggest that the eruption may have occurred in multiple stages rather than a single explosion. It is possible that several smaller outbursts occurred during the 2-decade eruption, gradually building the nebula we see today. Even more surprising is the amount of dust contained within the nebula. Dust forms when heavy elements expelled from the star cool and condense into tiny particles. The Homunculus Nebula contains an enormous quantity of this dust, enough to partially obscure the central star from view. In fact, the dust is one reason why Eta Carinae appears dimmer today than it did during the Great Eruption. Much of the star's light is absorbed or scattered by the surrounding cloud, but the nebula also performs an important role. It acts like a protective shield, absorbing large amounts of the intense radiation produced by the star. Without this surrounding cloud, the system might appear even brighter from Earth. As astronomers continued studying Eta Carinae throughout the 20th century, they realized something even more intriguing. The star had not returned to complete stability. Although the Great Eruption ended around 1858, the system still shows signs of ongoing activity. Occasional smaller eruptions have been observed. The star's brightness has fluctuated, and every 5.5 years, the interaction between the two stars produces dramatic changes in X-ray emissions. These periodic events provide valuable information about the structure of the system. When the two stars approach each other, their stellar winds collide with tremendous force. These collisions create enormous shock waves, heating gas to millions of degrees and producing bursts of high-energy radiation. By monitoring these emissions, astronomers can track the orbit of the stars and study the extreme physics occurring within the system. Despite all the progress in understanding Eta Carinae, one question continues to dominate scientific discussions. Is the star approaching its final explosion? The Great Eruption demonstrated that Eta Carinae is capable of releasing enormous amounts of energy without destroying itself. But massive stars do not live long. Eventually, their cores run out of fuel. When that happens, gravity takes over, and the result is one of the most powerful explosions in the universe. In the next part, we will explore what happens inside a massive star, like Eta Carinae, as it approaches the end of its life, and what kind of cosmic explosion it may eventually produce. To understand what may eventually happen to Eta Carinae, we first need to journey deep inside the star itself, far beneath the turbulent surface and the enormous clouds of gas that surround it. Because the true story of Eta Carinae is not only about the explosions we can see. It is about the invisible battle happening at its core. Like all stars, Eta Carinae exists because of a delicate balance between two powerful forces. Gravity pulls inward, trying to collapse the star under its own enormous mass. At the same time, nuclear fusion deep inside the core releases energy that pushes outward, creating pressure that supports the star against collapse. As long as these two forces remain balanced, the star remains stable. For stars like our Sun, this balance can last for billions of years, but Eta Carinae is not an ordinary star. It is a supermassive star, containing dozens of times the mass of our Sun. Because of this enormous mass, the pressure and temperature inside its core are far more extreme than anything found in smaller stars. Deep inside Eta Carinae's core, temperatures may exceed 40 million degrees Celsius. At such extreme temperatures, hydrogen atoms fuse together rapidly, forming helium and releasing vast amounts of energy. This process is the engine that powers the star. But in massive stars, this engine runs much faster. The Sun burns its hydrogen slowly and steadily, which is why it can shine for about 10 billion years. Eta Carinae, however, burns its fuel at an astonishing rate. Stars this massive may live only a few million years before reaching the final stages of their evolution. In other words, they burn incredibly bright, but their lives are short. As the hydrogen in the core begins to run out, the star undergoes a series of dramatic changes. The core begins to contract under gravity, becoming hotter and denser. Eventually, temperatures rise high enough for a new type of nuclear fusion to begin. Helium begins fusing into heavier elements such as carbon and oxygen. But this is only the beginning. Massive stars like Eta Carinae go through multiple stages of fusion during their lifetimes. After helium is exhausted, the core contracts again. Temperatures rise even further, allowing the fusion of even heavier elements. Carbon begins to fuse, then neon, then oxygen, and eventually silicon. Each stage produces heavier and heavier elements, and with each stage, the process becomes faster. The hydrogen burning phase may last millions of years. Helium fusion may last hundreds of thousands of years. Carbon burning may last only a few hundred years. By the time the star begins fusing silicon, the process may last only a few days. All of these reactions occur deep inside the star's core, creating a complex structure often compared to the layers of an onion. At the center lies the core, where the heaviest elements are formed. Surrounding it are shells, where lighter elements continue to fuse. Each layer produces energy that supports the star against gravity. But this structure cannot last forever. Eventually, the fusion process reaches its final stage. Iron. Iron is a special element in stellar physics. While fusion of lighter elements releases energy, fusion of iron consumes energy instead of producing it. That means once iron begins to accumulate in the core, the star's energy engine begins to fail. Without energy being produced in the core, the outward pressure that supports the star disappears. Gravity suddenly wins the battle, and when that happens, the collapse begins. In an instant, sometimes in less than a second, the core of the star collapses under its own gravity. Matter is compressed to extraordinary densities. The collapsing core rebounds violently, sending a powerful shockwave outward through the star. This shockwave tears the star apart in one of the most spectacular events in the universe, a supernova explosion. For a few brief weeks, the exploding star may shine brighter than an entire galaxy. The energy released in a single supernova can equal the energy produced by our Sun during its entire lifetime. And massive stars like Eta Carinae are almost certain to end their lives this way. But Eta Carinae may produce an explosion even more dramatic than a typical supernova, because its extreme mass places it in a category of stars capable of producing something even more powerful, a hypernova. Hypernova are rare events thought to occur when extremely massive stars collapse into black holes. During the collapse, enormous jets of energy may be launched from the poles of the star, blasting through the surrounding material at nearly the speed of light. These jets can produce some of the most energetic explosions ever observed. In some cases, they generate gamma-ray bursts, intense flashes of radiation that can be detected across billions of light-years of space. Gamma-ray bursts are among the most powerful explosions in the entire universe. For a few seconds, they can release more energy than our Sun will produce over its entire lifetime. Fortunately, not every massive star produces a gamma-ray burst. For that to happen, the jets produced during the collapse must be pointed directly toward Earth. If Eta Carinae were to produce such a burst aimed at our planet, the consequences could be severe. But astronomers believe this scenario is extremely unlikely. The orientation of the Eta Carinae system suggests that if a gamma-ray burst were produced, the jets would likely be pointed away from Earth. Even if Eta Carinae exploded tomorrow as a supernova, the distance between us, 7,500 light-years, would protect our planet from any harmful effects. Instead, we would witness one of the most spectacular astronomical events in recorded history. The explosion would become visible in the night sky as a brilliant new star. For weeks or months, it could shine brighter than any other star in the sky. Some estimates suggest it might even become bright enough to be seen during the daytime. Imagine looking up and seeing a new star glowing in the sky, one that had not been there before. For astronomers, it would be an extraordinary opportunity. Modern telescopes could observe the explosion across the entire electromagnetic spectrum, from radio waves to gamma rays. Scientists could watch in real time as the star collapsed and the shockwave expanded through space. It would be one of the most studied cosmic events in human history. But here is the strange part. Despite its violent past and enormous mass, Eta Carinae has not exploded yet. Even after the Great Eruption and centuries of observation, the star continues to survive, which means that something inside the star is still preventing the final collapse. And that raises one of the most fascinating questions in modern astronomy. How close is Eta Carinae to the end of its life? Is the star still thousands of years away from its final explosion? Or could it already be in the last stages of its evolution, quietly approaching the moment when gravity will finally win? The truth is that no one knows for certain, but astronomers have been carefully watching Eta Carinae for signs that the star may be changing again. And some of the observations they have made in recent decades suggest that the system may still hold surprises. In the next part, we will explore how modern telescopes are monitoring Eta Carinae today and what they have revealed about the violent environment surrounding one of the most unstable stars in the Milky Way. Even though the Great Eruption of Eta Carinae happened more than 170 years ago, astronomers are still studying its aftermath in extraordinary detail. In many ways, the system has become one of the most important natural laboratories for understanding how massive stars behave. Unlike many distant cosmic events that happened thousands or millions of years ago, the eruption of Eta Carinae occurred recently enough that we can still observe the expanding debris today. The material blasted into space during the 19th century continues to expand outward, forming the glowing structure known as the Homunculus Nebula. Modern telescopes have allowed scientists to examine this nebula with astonishing precision. When viewed through instruments like the Hubble Space Telescope, the Homunculus Nebula appears as two enormous lobes of gas expanding away from the central star. The structure resembles a giant cosmic hourglass with dense clouds of dust and gas forming bright glowing walls around an interior cavity. The nebula itself is made of material that once belonged to the star. During the Great Eruption, Eta Carinae expelled huge quantities of gas that cooled as they expanded into space. Over time, some of this gas condensed into microscopic dust particles, which now reflect and scatter the light coming from the star. This dust is one reason why the central star is so difficult to observe directly. Much of its light is hidden behind the thick clouds of material surrounding it. But while this dust blocks visible light, astronomers have found ways to study the system using other wavelengths. Infrared telescopes, for example, can detect heat radiating from the dust itself. Because the dust particles absorb light from the star and then re-emit it as heat, infrared observations reveal detailed structures hidden inside the nebula. These observations show complex layers of material moving outward from the star in different directions. Some regions contain dense clumps of gas. Others appear as thin filaments stretching across space. These structures tell scientists that the eruption was likely far more complicated than a single explosion. Instead, it may have involved multiple bursts of activity occurring over several years. Meanwhile, high-energy telescopes observing X-rays have revealed something equally fascinating happening near the center of the system. Eta Carinae is not just one star, it is a binary system, meaning two massive stars orbit each other. The larger star dominates the system, but the smaller companion star plays a crucial role in shaping what astronomers observe today. Both stars produce extremely powerful stellar winds. A stellar wind is a stream of charged particles flowing away from a star at incredible speeds. In the case of Eta Carinae, these winds are among the strongest known in the galaxy. The larger star produces a dense wind moving at about 500 kilometers per second. The smaller companion star produces a faster but thinner wind that can reach speeds of 3,000 kilometers per second. When these winds collide, the result is a violent shockwave. Imagine two enormous storms crashing into each other at thousands of kilometers per second. The collision compresses and heats the gas to temperatures of millions of degrees, producing intense X-ray radiation that can be detected from Earth. By studying these X-ray emissions, astronomers have been able to map the orbit of the two stars with remarkable precision. The stars complete one orbit around each other every 5.5 years, but their orbit is highly elongated, meaning they spend most of their time relatively far apart before swinging very close together. When the stars approach each other, their colliding winds become much more intense. This causes a dramatic increase in X-ray emissions as the shockwave between them grows stronger. But then, something strange happens. As the stars reach their closest point in the orbit, the X-ray signal suddenly drops. This sudden drop puzzled astronomers for many years. Eventually, scientists realized that during the closest approach, the dense wind from the larger star actually overwhelms the wind from the smaller star. The shockwave region collapses, temporarily shutting down the X-ray emission. Once the stars begin moving apart again, the shockwave reforms and the X-ray emissions return. These repeating cycles have allowed astronomers to track the system's behavior over decades. Every 5.5 years, the same pattern occurs. X-rays increase as the stars approach each other, then suddenly disappear during the closest encounter, then slowly return as the stars move apart again. This predictable cycle has made Eta Carinae one of the most carefully monitored stellar systems in the sky. But there is another reason scientists are watching it so closely. The system may still be evolving. In recent decades, astronomers have noticed subtle changes in the brightness and structure of the surrounding nebula. Some regions appear to be thinning. Others are expanding faster than expected. These changes suggest that the system may still be recovering from the Great Eruption. In addition, new observations have revealed smaller eruptions occurring within the system. These events are much weaker than the Great Eruption, but they show that the star remains unstable. Massive stars like Eta Carinae constantly lose material through their stellar winds. Over time, this process gradually reduces the mass of the star. This mass loss can significantly influence how the star will eventually die. Some massive stars lose so much material that they end their lives as Wolf-Rayet stars, extremely hot stars with strong winds that strip away their outer layers. Others retain more of their mass and explode in extremely powerful supernovae. Eta Carinae may still be somewhere between these possibilities. Its future depends on how much mass it continues to lose in the coming thousands of years. The presence of the companion star adds even more complexity. Gravitational interactions between the two stars may trigger additional eruptions or influence how the final collapse occurs. Some astronomers believe the companion star may even play a role in shaping the eventual supernova explosion. If jets form during the collapse, the orbital interaction between the stars could affect their direction. All of this makes Eta Carinae a remarkably complicated system. It is not just one unstable star. It is a dynamic environment filled with powerful winds, expanding nebulae, gravitational interactions, and ongoing eruptions. And every year, astronomers learn a little more about how it behaves. Space telescopes such as Hubble, Chandra, and James Webb continue to observe the system across different wavelengths of light. Each new observation reveals more details about the structure of the nebula and the interactions between the stars. But despite all these observations, one question remains impossible to answer with certainty. When will Eta Carinae finally explode? The star may still have thousands, or even tens of thousands, of years left before its core collapses. But massive stars evolve quickly, and Eta Carinae has already shown that it behaves in ways that surprise astronomers. which means its final explosion could come sooner than expected, or it may continue erupting for centuries before finally reaching the end. Either way, Eta Carinae remains one of the most closely watched stars in our galaxy, because whenever that final moment arrives, astronomers across the world will be ready, and when it happens, the explosion may become one of the most spectacular cosmic events humanity has ever witnessed. In the next part, we will explore what the night sky might look like if Eta Carinae finally explodes, and how such an event would appear from Earth. For nearly 2 centuries, astronomers have been watching Eta Carinae with a mixture of fascination and anticipation. The reason is simple. Stars like Eta Carinae do not live forever. Their immense mass ensures that their lives burn fast and violently, and eventually they must come to an end. And when a star as massive as Eta Carinae dies, the event is anything but quiet. It will end in a cosmic explosion powerful enough to reshape the surrounding region of space. But the real question astronomers often ask is this: what would it look like from Earth if Eta Carinae exploded? To answer that, we first need to remember how far away the star actually is. Eta Carinae lies approximately 7,500 light-years from Earth. That may sound incredibly distant, and it is, but in astronomical terms, it is still within our own galaxy. This means that if the star exploded, the event would be easily visible from our planet. In fact, it would become one of the most dramatic astronomical spectacles humans have ever seen. When a massive star collapses and explodes as a supernova, the brightness of the explosion increases enormously. For a brief period, the exploding star can outshine every other star in the galaxy. To understand the scale of this brightness, imagine the entire lifetime of the Sun. Over about 10 billion years, our Sun will steadily release energy as it converts hydrogen into helium. A supernova can release a comparable amount of energy in just a few seconds. That energy spreads outward in all directions as a shockwave traveling through the star's outer layers. As the shockwave tears the star apart, enormous quantities of gas are blasted into space at speeds of thousands of kilometers per second. The expanding debris glows intensely as it heats surrounding gas and dust. For weeks or even months, the explosion can remain incredibly bright. If Eta Carinae were to explode today, astronomers estimate that it could briefly become one of the brightest objects in our sky. Some estimates suggest it might appear nearly as bright as Venus. Others suggest it could even rival the brightness of the Moon, although this depends on the exact nature of the explosion. If it reached that brightness, the star might even become visible during the daytime. Imagine stepping outside and seeing a new brilliant star shining in the sky, a star that had never been there before. For people living in the southern hemisphere, Eta Carinae would become a spectacular sight. The constellation Carina, where the star resides, would suddenly contain a brilliant new beacon. For observers in the northern hemisphere, the star would remain below the horizon, hidden from view. But the scientific importance of the explosion would be enormous. Modern astronomy is equipped with instruments that were unimaginable when the Great Eruption occurred. Today, we have telescopes capable of observing across the entire electromagnetic spectrum, from radio waves to gamma rays. If Eta Carinae exploded, astronomers could monitor the event in real time. Space telescopes such as Hubble, Chandra, and James Webb would observe the expanding shockwave and the behavior of the surrounding nebula. Radio telescopes would track the expanding debris cloud as it collided with interstellar gas. Particle detectors could even capture streams of neutrinos, tiny particles released during the collapse of the star's core. In fact, neutrinos might be the very first signal astronomers detect. Because neutrinos interact very weakly with matter, they can escape from the collapsing core of the star before the explosion becomes visible. Large underground detectors on Earth, such as Super Kamiokande in Japan, could detect a burst of neutrinos hours before the light from the explosion reaches us. This would provide scientists with an early warning that a supernova had just occurred somewhere in our galaxy. Shortly afterward, telescopes across the world would turn toward the constellation Carina, and the sky would suddenly contain a new, brilliant star. The explosion would likely remain visible for weeks or months as the expanding debris cloud continued glowing. Eventually, the brightness would begin to fade, but the story would not end there. The expanding debris from the explosion would continue spreading outward through space, forming a new supernova remnant. Over centuries or thousands of years, this remnant would become a glowing cloud of gas similar to famous objects such as the Crab Nebula. Future civilizations might one day look toward the Carina Nebula and see the expanding remains of the explosion. But despite the spectacular nature of such an event, there is an important question many people ask. Would an explosion of Eta Carinae pose any danger to Earth? The reassuring answer is no. Although the explosion would release an enormous amount of energy, the distance between Earth and Eta Carinae is simply too great for the event to cause any harm. At 7,500 light-years away, the energy from the explosion would spread out over a vast region of space before reaching our planet. By the time it arrived here, it would appear only as a brilliant new star in the sky. The situation would be very different if a supernova occurred much closer. Astronomers believe that a supernova within 30 light-years of Earth could potentially damage our planet's atmosphere by exposing it to intense radiation. Fortunately, no stars that close to Earth appear capable of exploding in the near future. Eta Carinae is hundreds of times farther away than that danger zone. So while the explosion would be spectacular, it would also be completely safe. But there is one more possibility astronomers sometimes discuss. Some extremely massive stars collapse into black holes while producing narrow beams of intense radiation known as gamma-ray bursts. Gamma-ray bursts are among the most energetic explosions in the universe. For a few seconds, they can release more energy than the sun will produce during its entire lifetime. If such a burst were directed toward Earth from a relatively close star, it could potentially damage the atmosphere. However, astronomers studying Eta Carinae believe this scenario is extremely unlikely. Gamma-ray bursts occur when jets of energy shoot out from the poles of a collapsing star. In order for Earth to be affected, those jets would need to be pointed directly toward our planet. Observations of Eta Carinae's orientation suggest that any such jets would likely be aimed away from Earth. Even if a gamma-ray burst occurred, our planet would almost certainly be outside the path of the radiation. So for us, the explosion would remain a beautiful cosmic event rather than a dangerous one. And for astronomers, it would represent an extraordinary opportunity. Supernovae in our own galaxy are extremely rare. The last clearly observed supernova in the Milky Way occurred in 1604, when the astronomer Johannes Kepler recorded a bright new star appearing in the sky. Since then, most supernovae have been observed only in distant galaxies. If Eta Carinae exploded within the next few centuries, it would become the first naked-eye supernova visible in our galaxy in over 400 years. And thanks to modern technology, scientists would be able to study it in ways that early astronomers could never have imagined. But there is still one mystery left. Despite its violent past and unstable nature, Eta Carinae continues to survive. It has already erupted once in a spectacular event, and yet the star remains intact, which means that somewhere inside this enormous stellar giant, the delicate balance between gravity and nuclear fusion still holds, for now. But eventually, that balance must break, and when it does, Eta Carinae may finally reveal its true power. In the next part, we will explore what might happen to the star after the explosion, and what kind of object could remain at the center of the cosmic debris. When a star finally reaches the end of its life, the explosion itself is only part of the story. The true mystery often lies in what remains after the light fades. In the case of Eta Carinae, the question is especially fascinating because the star is so massive that its final fate could follow more than one path. Unlike smaller stars such as our Sun, which quietly shed their outer layers and become white dwarfs, extremely massive stars end their lives in violent collapses. Their cores are crushed by gravity until matter itself can no longer resist the pressure. And when that happens, one of the most extreme objects in the universe is born. But the exact outcome depends on the mass of the star's core at the moment it collapses. In some cases, the collapsing core becomes a neutron star. In other cases, it forms a black hole. Eta Carinae is so massive that astronomers suspect its final destination may almost certainly be a black hole. But understanding how that transformation happens requires looking deep into the final seconds of a dying star. Inside a massive star like Eta Carinae, nuclear fusion has been occurring for millions of years. At the beginning of the star's life, hydrogen fuses into helium in the core, releasing enormous energy that pushes outward against gravity. This balance between outward pressure and inward gravity is what keeps the star stable. But hydrogen does not last forever. Eventually, the star begins fusing heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon. Then silicon. Each stage produces less energy and lasts for a shorter time. For extremely massive stars, the final stages of nuclear burning occur astonishingly quickly. The last fusion stage, silicon burning, may last only a few days. During this phase, silicon nuclei fuse together to form iron, and iron marks the end of the road. Unlike lighter elements, iron cannot release energy through fusion. Instead, fusing iron actually consumes energy. This means that once the star's core becomes dominated by iron, the engine that has supported the star for millions of years suddenly stops working. Without that energy pushing outward, gravity immediately takes over. The core begins collapsing inward at incredible speed. Within seconds, The core can shrink from a size comparable to Earth to a sphere only about 20 kilometers across. The collapse is so violent that electrons and protons are crushed together, forming neutrons. The result is a dense ball of matter where a single teaspoon could weigh billions of tons. This object is what astronomers call a neutron star. But if the collapsing core is massive enough, even neutron matter cannot stop the collapse. Gravity continues crushing the core until it forms something even more extreme, a black hole. At that point, the gravitational pull becomes so strong that nothing, not even light, can escape. The boundary surrounding this region is known as the event horizon. Anything that crosses this boundary is permanently trapped. For Eta Carinae, the core mass at the time of collapse will determine which of these outcomes occurs. But because the star is thought to have originally contained more than 100 times the mass of the Sun, many astronomers believe the formation of a black hole is the most likely result. However, the process may not be straightforward. Before the final collapse occurs, the star may experience additional eruptions similar to the Great Eruption of the 1840s. These eruptions can remove large amounts of mass from the star. In fact, the Homunculus Nebula surrounding Eta Carinae contains material that was violently expelled during that earlier outburst. This loss of mass can significantly change the star's fate. If enough material is shed before the collapse, the remaining core might be small enough to produce a neutron star instead of a black hole. But if the core remains extremely massive, the collapse could create one of the most powerful black holes ever formed in our galaxy. Some astronomers even suspect that Eta Carinae could produce what is known as a collapsar. A collapsar occurs when a massive star collapses directly into a black hole while still rotating rapidly. The collapsing material forms an accretion disk around the newborn black hole. Enormous magnetic fields can then channel energy into narrow jets that shoot out from the star's poles. These jets are what produce gamma ray bursts, the most energetic explosions known in the universe. For a few seconds, a gamma ray burst can release more energy than the Sun will emit in its entire 10 billion year lifetime. Fortunately, as we discussed earlier, the orientation of Eta Carinae appears to make it unlikely that such jets would point toward Earth. But even without a gamma ray burst, the collapse of the star would still produce a spectacular supernova explosion. After the explosion, the expanding debris would form a glowing shell of gas that continues expanding through space. This shell would gradually interact with the surrounding material in the Carina Nebula. Shockwaves traveling through this gas would heat it to millions of degrees, causing it to glow in X-rays. Over time, this expanding cloud would become a new supernova remnant. Inside that remnant, hidden at the center, would be the compact object left behind by the collapse. If the core becomes a neutron star, it may also become something known as a pulsar. Pulsars are rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like the beam of a lighthouse. If Earth happens to lie in the path of these beams, we detect regular pulses of radio waves. Some pulsars rotate incredibly fast, the fastest known spin hundreds of times per second. But if Eta Carinae collapses into a black hole instead, the story becomes even more mysterious. A newly formed black hole would initially be surrounded by enormous amounts of gas. from the exploding star. As this gas spirals inward toward the event horizon, it forms a glowing accretion disk. The material in the disk becomes incredibly hot as it accelerates under the intense gravitational pull. Friction and magnetic forces heat the gas to millions of degrees. This hot material emits powerful radiation, particularly in X-rays. For a time, the newborn black hole could become one of the brightest X-ray sources in our galaxy. Eventually, however, the surrounding gas would disperse. The expanding supernova remnant would continue growing larger, and the black hole at the center would quietly remain hidden within the expanding cloud of debris. But its presence could still be detected through its gravitational influence on nearby material. Astronomers could observe how gas moves around the invisible object. By studying these motions, they could confirm the presence of the black hole. Over thousands of years, the remnant of Eta Carinae would slowly expand outward. The gas ejected during the explosion would enrich the surrounding region of space with heavy elements. This process is one of the most important ways the universe creates the materials necessary for planets and life. Elements such as iron, calcium, oxygen, and silicon are forged inside massive stars. When those stars explode, these elements are scattered across interstellar space. Eventually, some of that material becomes part of new stars and planetary systems. In fact, the atoms in your own body were once forged in ancient stellar explosions. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of these elements were created in stars that lived and died long before the sun was born. So when Eta Carinae finally reaches the end of its life, it will not simply disappear. Instead, it will help shape the future of the galaxy. The elements created inside its core will be scattered into space, becoming the raw material for future generations of stars and planets. But there is another remarkable aspect of Eta Carinae that scientists continue to study today. The star is not alone. It is actually part of a binary system, meaning two stars orbit each other. The companion star, known as Eta Carinae b, is itself extremely massive. It likely contains around 30 to 60 times the mass of the Sun. The two stars orbit each other every 5.5 years, moving through the dense clouds of gas surrounding them. Their powerful stellar winds collide with enormous force, producing shockwaves that emit X-rays detectable from Earth. This interaction has provided astronomers with valuable information about the structure of the system. But it also raises an interesting question. What will happen to the companion star when Eta Carinae finally explodes? When the primary star collapses and explodes, the sudden loss of mass could dramatically alter the gravitational balance of the system. The companion star might be flung into space at tremendous speed, or it might continue orbiting the newly formed black hole. If the two objects remain gravitationally bound, the system could eventually become an X-ray binary. In such systems, gas from the companion star can fall toward the black hole, producing intense radiation. These systems are among the most energetic objects in the galaxy. So even after Eta Carinae dies, the system could remain active for millions of years. A black hole and a massive companion star orbiting each other in the glowing remains of a supernova explosion. But all of this remains speculation for now. Eta Carinae is still alive, still unstable, still evolving, and every year astronomers continue to observe it carefully. searching for signs that the star may be approaching its final moments. In the next part, we will explore one of the most fascinating questions of all. Could Eta Carinae already be close to exploding right now? And if it did explode today, when would we actually see it? When we look at the night sky, it feels like we are seeing the universe exactly as it exists at that moment. The stars appear fixed and constant, shining steadily above us as if nothing ever changes. But this is one of the greatest illusions in astronomy. Because light does not travel instantly, every time we look at a star, we are actually looking into the past. The light reaching our eyes today may have left that star years, centuries, or even thousands of years ago. And in the case of Eta Carinae, this fact creates a remarkable possibility. The star lies about 7,500 light-years from Earth. That means the light we see today began its journey toward us roughly 7,500 years ago. When that light left Eta Carinae, human civilization was still in its earliest stages. The pyramids of Egypt had not yet been built. Agriculture was only beginning to spread across many regions of the world. Entire cultures and empires that we know from history had not yet existed. And yet, the light from Eta Carinae had already started its long journey across the galaxy. Which leads to a fascinating thought. If something dramatic happened to Eta Carinae after that light left the star, we would not know about it yet. In other words, Eta Carinae could already have exploded, and we simply have not seen it happen. This idea may sound surprising at first, but it is actually a common situation in astronomy. When astronomers observe distant objects, they are always seeing them as they existed in the past. For galaxies millions of light-years away, we see them as they looked millions of years ago. For objects billions of light-years away, we see them as they looked when the universe itself was much younger. But even within our own galaxy, the same principle applies. The light from Eta Carinae takes thousands of years to cross the distance between the star and Earth. So if the star exploded today, we would not see that explosion until the year around 9,500 AD. And if the star exploded 3,000 years ago, the light from that explosion might still be traveling toward us right now. It could already be on its way across the Milky Way. This possibility leads to an extraordinary scenario. At some moment in the future, perhaps tomorrow, perhaps centuries from now, the sky could suddenly reveal a brilliant new star, and that light would actually be the delayed signal of an explosion that occurred thousands of years in the past. Of course, this does not mean astronomers believe the explosion has already happened. There is no evidence suggesting that Eta Carinae has recently collapsed, but the idea highlights how time works in astronomy. The universe we observe is always a record of the past. Still, scientists continue to monitor Eta Carinae carefully, searching for signs that the star may be approaching its final stages. One of the ways they do this is by studying the stellar winds flowing away from the star. Eta Carinae produces some of the most powerful stellar winds ever observed. These winds carry enormous amounts of material away from the star at speeds reaching thousands of kilometers per second. In fact, the star loses mass so quickly that it may shed an amount of material equal to the mass of Earth every year. This constant loss of material plays a critical role in determining how the star will eventually die. The more mass the star loses, the smaller its core becomes, and the size of that core determines whether the star ends its life as a neutron star or a black hole. Astronomers also study the behavior of the Homunculus Nebula, the massive cloud of gas expelled during the Great Eruption. This nebula continues expanding outward into space. By measuring its motion and structure, scientists can learn more about the forces that shape the eruption. These observations help astronomers understand how unstable Eta Carinae truly is. Another important clue comes from the star's binary companion. Eta Carinae is not alone. A second massive star orbits it every 5.5 years, passing through the dense stellar wind surrounding the primary star. When the two stars come closest to each other in their orbit, their powerful winds collide. This collision produces intense bursts of X-rays, which astronomers detect with space telescopes. By monitoring these X-ray emissions, scientists can track changes in the system. If the behavior of the winds or the orbit suddenly changed, it could signal that something unusual was happening inside the star. But so far, the system appears to be continuing its complex dance without any immediate signs of collapse. Still, massive stars often behave unpredictably during the final stages of their lives. Some stars appear relatively stable for long periods before suddenly experiencing violent eruptions. Others undergo dramatic changes in brightness shortly before exploding. Astronomers studying Eta Carinae are particularly interested in the possibility that the star belongs to a class known as luminous blue variables. These stars are famous for their extreme instability. They can dramatically increase their brightness and eject huge amounts of material into space. The Great Eruption of Eta Carinae in the 1840s is one of the most famous examples of this behavior. But events like that may actually represent the final stages of a massive star preparing for its ultimate collapse. In some cases, stars have been observed undergoing large eruptions only years or decades before exploding as supernovae. If Eta Carinae follows a similar path, its dramatic outburst in the 19th century could have been part of a long series of destabilizing events leading toward the final explosion. However, predicting exactly when that explosion will occur is extremely difficult. Astronomers estimate that Eta Carinae could explode sometime within the next 100,000 years. That might sound like a very long time, but in the life of a massive star, it is actually quite close to the end. Stars like Eta Carinae live fast and die young. While smaller stars can shine for billions of years, extremely massive stars may exist for only a few million years. Eta Carinae is already believed to be several million years old, which means that, in cosmic terms, it is nearing the end of its life. But even within that final stage, the exact timing remains uncertain. The explosion could happen tomorrow, or it might occur tens of thousands of years from now. From a human perspective, that difference is enormous. From the perspective of the universe, it is almost insignificant. And so, astronomers continue watching. Every year, telescopes observe the star in visible light, infrared radiation, X-rays, and other wavelengths. They measure changes in brightness. They track the motion of the surrounding nebula. They analyze the behavior of the binary companion. All of these observations provide clues about the complex processes happening deep inside the star. And every observation brings us a little closer to understanding how such enormous stars evolve. But the most exciting possibility remains the same. One day, perhaps unexpectedly, the sky could suddenly reveal a brilliant new star, a star that was not there the night before, a star bright enough to rival the brightest objects in the sky. And when that moment arrives, humanity will witness one of the most powerful events in the entire universe, the final explosion of a star that has fascinated astronomers for centuries. But before that happens, there is one final question to consider. When Eta Carinae eventually explodes, what will the explosion actually look like from Earth? Will it appear suddenly? Will it grow brighter over time? And how long will the spectacle last in our sky? In the next part, we will explore exactly how the night sky might change when one of the most massive stars in our galaxy finally reaches the end of its life. For most of human history, the night sky has appeared calm and unchanging. The same constellations rise and set. The same stars return year after year. But occasionally, the universe reminds us that the sky is not static at all. Throughout history, astronomers have recorded moments when a new star suddenly appeared where none had been seen before. In ancient China, careful sky watchers documented mysterious guest stars that shone brightly for weeks or months before fading away. Centuries later, we would understand what those observers were witnessing. They were seeing supernova explosions, the violent deaths of massive stars. If Eta Carinae were to explode, humanity would experience something very similar. But unlike those ancient observers, we would witness the event with modern technology. Telescopes on Earth and in space would immediately begin studying every detail of the explosion. And for people looking up at the sky, the change could be dramatic. Because Eta Carinae sits inside the Carina constellation, a region of the sky visible mainly from the southern hemisphere. Countries such as Australia, South Africa, Chile, Argentina, and New Zealand would have the best view of the event. Observers in the northern hemisphere might not see the explosion at all, since the star lies too far south. But for those who could see it, the spectacle might be unforgettable. At first, the explosion would likely appear as a new bright star suddenly emerging in the sky. Unlike the steady glow of ordinary stars, a supernova brightens extremely quickly. Within hours or days, the star could increase its brightness by thousands or even millions of times. What had once been an ordinary point of light would suddenly dominate the constellation around it. At its peak brightness, Eta Carinae might shine as brightly as Venus, which is often the brightest object in the night sky after the moon. In some scenarios, astronomers believe it could even approach the brightness of the moon itself, though this is less certain. If that happened, the explosion could briefly become visible even during the daytime. Imagine stepping outside during the day and noticing a strange new point of light shining against the blue sky. That is how bright a nearby supernova can become. But the spectacle would not end after a single night. Supernova explosions evolve over time. During the first few days, the brightness rises rapidly as the shockwave from the collapsing core blasts through the outer layers of the star. Once the shockwave reaches the surface, enormous amounts of energy are released into space. The star's outer atmosphere is hurled outward at tremendous speeds. As the expanding material glows with heat and radiation, the brightness of the explosion reaches its peak. This stage may last several weeks. During that time, the star would appear as a brilliant beacon in the sky. People living under dark skies in the southern hemisphere might easily spot it without any telescope. Even from cities, the explosion could remain visible. Then, slowly, the brightness would begin to fade, but the fading process might take months or even years. After the initial flash, the glow of the explosion is powered by radioactive elements created during the collapse. One of the most important of these elements is nickel-56. This unstable isotope decays into cobalt and then into iron. As it decays, it releases energy that keeps the expanding debris glowing. That radioactive energy slowly diminishes over time, causing the light from the supernova to gradually fade. But even as the brightness decreases, something remarkable begins to appear. The expanding debris from the explosion forms a growing cloud of gas and dust. Under powerful telescopes, astronomers would begin to see the structure of the explosion itself. Filaments of glowing gas, expanding shock waves, complex patterns formed by the violent forces unleashed during the collapse. These structures would slowly expand outward over the years. Eventually, the explosion would become what astronomers call a supernova remnant. Famous examples of these remnants already exist in our galaxy. One of the best known is the Carina Nebula, which formed after a supernova explosion recorded by Chinese astronomers in the year 1054. Today, the Carina Nebula appears as a delicate cloud of glowing gas expanding outward from the center of the explosion. At its core lies a rapidly spinning neutron star, the collapsed remains of the original star. If Eta Carinae exploded, it would likely create a similar remnant. However, because the star is surrounded by the material expelled during its earlier eruptions, the explosion would interact with that material in complex ways. The expanding shockwave would slam into the gas of the Homunculus Nebula, heating it to extreme temperatures. That interaction would produce intense radiation across many wavelengths. Astronomers would observe powerful bursts of X-rays as the shockwave collided with the surrounding clouds. Infrared telescopes would detect glowing dust heated by the explosion. Radio telescopes would track the expanding shell as it spread through the nebula. For scientists, this would be an extraordinary opportunity because supernova explosions within our own galaxy are extremely rare. The last confirmed naked-eye supernova in the Milky Way occurred in 1604, when the astronomer Johannes Kepler recorded a bright new star appearing in the sky. Since then, most supernovae we observe occur in distant galaxies. They are visible only through telescopes, but an explosion as close as Eta Carinae would allow astronomers to study the process in unprecedented detail. Every stage of the explosion could be observed. Every change in brightness could be measured. Every shockwave could be tracked. And this would not only happen in visible light. Modern observatories detect many different forms of radiation. Before the explosion becomes visible, detectors on Earth might record a sudden burst of neutrinos. Neutrinos are nearly massless particles that are produced in enormous quantities during the collapse of a star's core. Because they interact very weakly with matter, they escape the star almost immediately. Large underground detectors, such as Super Kamiokande in Japan, are capable of detecting these particles. If Eta Carinae collapsed, these detectors might register a burst of neutrinos hours before the explosion becomes visible in the sky. That would give astronomers a brief warning that something extraordinary had just happened. Soon afterward, the light from the explosion would arrive. Then another signal might follow. When the core collapses, it can produce tiny ripples in the fabric of space-time itself. These ripples are called gravitational waves. Advanced observatories like LIGO and Virgo are designed to detect these waves. If Eta Carinae produced a strong enough signal, it could be detected by these instruments. That would allow scientists to observe the explosion not only through light, but also through gravitational waves and neutrinos. In other words, the death of Eta Carinae would become a multi-messenger event, one of the most valuable kinds of observations in modern astronomy. For months or years after the explosion, telescopes across the world would continue studying the expanding debris. Scientists would measure how fast the gas is moving. They would analyze the chemical composition of the material. They would search for signs of the compact object left behind in the center. And slowly, the brilliant new star in the sky would fade away. Eventually, it would no longer be visible to the naked eye, but its expanding cloud of debris would remain. Over centuries, the remnant would grow larger and larger, spreading through the surrounding region of space. Future generations might look toward the Carina Nebula and see a glowing cloud marking the place where a giant star once died. But there is something else worth considering. When such explosions occur, they remind us that the universe is constantly changing. Stars are born, stars evolve, and eventually stars die. But those deaths are not the end of the story, because the material scattered by supernova explosions becomes the building blocks of new stars and planets. Every atom of iron, every atom of calcium, every atom of oxygen, all of these elements were created inside stars that exploded long before the sun was born. In that sense, the death of a star is also the beginning of something new. And when Eta Carinae finally reaches that moment, its explosion will send newly forged elements into space, elements that may one day become part of future worlds, or perhaps even future forms of life. But before we conclude our exploration of this remarkable star, there is one final perspective to consider. Because Eta Carinae is not just a fascinating object in astronomy, it is also a reminder of how extreme the universe can be. In the final part, we will step back and look at what Eta Carinae teaches us about the life cycles of stars and about our place in a universe filled with colossal forces beyond imagination. When we talk about Eta Carinae, it's easy to focus only on the drama: a massive star, violent eruptions, a future explosion powerful enough to briefly rival the brightness of the moon. But behind all of that spectacle lies something deeper. Eta Carinae is not just an unstable star waiting to explode. It is part of a much larger story, the story of how the universe evolves. Because the life and death of massive stars are among the most important processes shaping the cosmos. Without them, the universe would be a very different place. To understand why, we have to think about what stars actually do during their lifetimes. Inside the core of a star, nuclear fusion slowly transforms simple elements into heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. And in the most massive stars, this chain continues all the way to iron. Each step in this process releases energy. That energy is what allows stars to shine, but it also creates the elements that eventually become part of planets, atmospheres, oceans, and living organisms. When stars first formed after the Big Bang, the universe contained almost nothing but hydrogen and helium. There was no carbon, no oxygen, no iron, no calcium, none of the elements required to build complex structures like planets or life. Those elements had to be created somewhere, and that somewhere was inside stars. Massive stars like Eta Carinae are especially important because they produce the heaviest elements, but those elements remain locked inside the star for most of its life. Only when the star dies are they released into space, and the way they are released is through one of the most violent events in the universe, a supernova. When a massive star explodes, the energy of the explosion scatters enormous amounts of material into the surrounding galaxy. Gas and dust enriched with heavy elements are thrown outward at incredible speeds. Over time, this material mixes with the interstellar medium. The vast clouds of gas and dust that fill the spaces between stars. Eventually, some of those clouds collapse under their own gravity. New stars begin to form. Around those stars, disks of dust and gas gather into planets, and those planets inherit the elements forged in earlier generations of stars. In other words, the death of one star helps create the conditions for entirely new solar systems to emerge. In fact, the atoms in your own body were once part of ancient stellar explosions. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of these elements were created inside massive stars that lived and died billions of years ago. So when Eta Carinae eventually explodes, it will become part of that same cosmic cycle. Its explosion will enrich the Carina Nebula with heavy elements. Those elements will spread through the surrounding region of the galaxy, and someday, long after the explosion has faded from the sky, that material may become part of new stars and new planets, perhaps even new forms of life. But there is something else Eta Carinae teaches us. It reminds us that the universe is filled with extremes far beyond anything we experience on Earth. The star itself is a giant on a scale that is difficult to comprehend. Its mass once exceeded 100 suns. Its luminosity is millions of times greater than the sun. Its stellar winds carry away enormous quantities of matter every year, and its past eruption briefly made it one of the brightest stars in the entire sky. Yet even something as enormous and powerful as Eta Carinae is temporary. Stars do not last forever. Even the largest and most luminous eventually run out of fuel, and when they do, gravity takes over. The delicate balance that sustained the star for millions of years collapses. What follows is a brief but spectacular end, an explosion so powerful that it can be seen across the galaxy. But even that explosion lasts only a short time, weeks, months, perhaps a few years. Then the light fades. The expanding debris spreads outward into space, and eventually, the star that once dominated its region of the sky becomes nothing more than a cloud of glowing gas. This cycle of birth, evolution, and destruction happens constantly throughout the universe. At any moment, somewhere in the cosmos, a star is forming inside a collapsing cloud of gas. Elsewhere, another star is quietly aging. And somewhere else, a star is reaching the end of its life and exploding. The universe is not static. It is a dynamic and ever-changing place. Eta Carinae is simply one of the most dramatic examples of that process happening within our own galaxy. And that is one reason astronomers find it so fascinating. Because by studying stars like Eta Carinae, we learn more about how the universe works. We learn how stars evolve, how they explode, and how they influence the galaxies around them. But there is also a more philosophical aspect to this story. When we look at Eta Carinae through a telescope, we are witnessing an object thousands of light years away. The light reaching our eyes tonight left the star long before human civilization reached its modern form. And yet, that distant star has helped shape the very matter from which we are made. The atoms in our bodies were once part of ancient stars, stars that lived and died long before the sun existed. In a very real sense, we are connected to the same cosmic processes that are unfolding inside Eta Carinae today. The universe is not something separate from us. We are part of it. The same physical laws that govern the lives of stars also govern the atoms in our own bodies. And that connection is one of the most profound discoveries of modern science. It means that when we study stars, we are also learning something about ourselves, about where we came from, and about the long chain of events that made life on Earth possible. So when Eta Carinae finally explodes, whether that happens tomorrow, thousands of years from now, or long after humanity has disappeared, it will not simply mark the end of a star. It will mark another step in the ongoing story of the universe, a story that began billions of years ago and continues unfolding across the vastness of space. Perhaps one day, future civilizations will look toward the Carina Nebula and see the glowing remains of Eta Carinae's final explosion, a beautiful cloud of gas expanding slowly through the darkness. And they will know that long before their time, a giant star once lived there, a star so massive and unstable that it fascinated astronomers for centuries, a star that erupted violently in the 19th century, a star that scientists watched carefully, wondering when its final moment would arrive. And when that moment finally came, it briefly lit up the sky before fading into the quiet background of the galaxy. Just another reminder that even the most powerful objects in the universe are part of an endless cosmic cycle: birth, life, death, and rebirth among the stars. If you enjoy exploring the mysteries of space and the quiet beauty of the cosmos, consider subscribing to Theories Before Sleep, because beyond Eta Carinae, countless other mysteries are waiting in the darkness, and the universe always has another story to tell.